Greetings, everyone. I hope you brought your triangles because it's time to do some trigonometry. Now we're going to start talking about derivatives of trig functions. We're going to start with the two main ones that pretty much build all of the rest of the rules from sine and cosine. We hinted already when we were doing some of the graphs a couple of lectures ago. The derivative of sine is cosine, and the derivative of cosine is negative sine. Let's say it a little bit more officially, sine of x, right? The derivative is cosine of x. Derivative of cosine of x is negative sine of x, right? Now remember, most of the time when we're dealing with trig, especially in calculus, the x is going to be measured in radians, not degrees. Now that's not saying we couldn't, it's just that we all have all of our connections to our realities through radians, okay? So you should expect all of the angular variables to be measured in radians, more of a realistic measurement, okay? So real quick, let's talk about why these derivatives are the way they are, so we can say we've officially seen that and we can use them, right? So I set up my difference quotient, like before, using the definition of derivative. And when I have sine of x plus h, I use one of the trig identities, the sine of a sum identity. Sine of x plus h is sine x cosine h plus cosine x sine h. One of your old trig identities. That's why I said I hope you brought your triangles and trig knowledge, right? There's going to be quite a bit of it. You need to be up on all of your trig identities. Okay? Of course, the minus sine x is still there. And what I do from here is I notice the sine x here and the sine x here. I can rearrange this so that I factor a sine x out. And when I do, I'm left with cosine of h minus 1. And then I just split off the over h. Now the reason I did that is because the limit as h goes to 0 of cosine h minus 1 over h is a limit that we did way back, right? We even proved it a couple of different ways with the pattern and with some actual algebra of limits, okay? So we remember that this limit value is 0, so this whole chunk is going to wipe out. And then what's left over is cosine x times sine of h divided by h. And again, the limit as h goes to 0 of sine h over h is 1. That was the major one that we proved using triangles and the squeeze theorem, right? That was this one. Since it's equal to 1, we just have cosine x times 1, which is cosine x. The proof for the cosine one is practically the same thing. You just start with a cosine difference quotient, and you still use your sum identity to split up the cosine. You get the cosine x's together to factor, and look, you have those same two limits as before. The only difference is they have different things multiplied by them. So this one gets zeroed out, and this one goes to 1. So we're left with the negative sine x. Okay? So we have our two main trig derivatives there, right? Sine goes to cosine goes back to negative sine. So imagine if you had to do several of these derivatives. I call it the sine cosine derivative ladder, right? Sine derivative is cosine, then down to negative sine. But from here, if I were going to do a derivative again, remember that derivative of sine is cosine, and the negative is just a multiplied number in front that's just along for the ride. So derivative of negative sine is negative cosine, but derivative of cosine is negative sine, but I've already got a negative, so it would be negative negative, which is positive. And notice I get back to sine x, which is where we started, right? So by the time you've done 4 derivatives, you've gotten back to where you started with these trig functions here. So that's why I call it the ladder. It's just repeating the same 4 steps over and over and over again. Okay? All right, so let's get an example in. find the second derivative of y if y is equal to 5x squared times sine x. Okay? Now look at it and think to yourself, what do I see? Right? I see the sine x, but you also need to see the 5x squared here, right? This is a multiplication, not an addition. So I'm not going to do just the 5x squared and the sine x separately and move on. No. This is a product rule. Okay? Now this is where that product rule really starts to sink in. Yes, I really need this because I can't simplify this any other way. This isn't some of the polynomials that we did before where it's like, I could do it with the product rule or I could just simplify it. No. This is going to be one that you have to do with the product rule because it is what it is. That's as simplified as it's going to get. So I have my first part and my second part there, right? Remember the product rule is each one gets a term with the derivative while the other does not. So my first derivative, y prime, I'll do the derivative of the front, that's 10x. Leave the second guy alone, that's sine x. Plus, leave the first guy alone, 5x squared. Derivative of the second guy, sine x derivative is cosine x. Okay, from here, anything that I can simplify? Not really. There's no like terms. I suppose we could factor, but you should probably wait on that to the end. Okay? So, it wants a second derivative now. A second derivative is going to entail me recognizing that this is an addition, right? So I'm going to do this and I'm going to do this separately. But each one of those is a product rule. So I've got to do this product rule and then plus, and then I'll have two more terms from that product rule. Okay, so here we go. Derivative of 10x is 10. Leave the sine alone. Plus, leave the 10x alone. Derivative of sine x is cosine x. Now I put this plus in. Now I do this product rule. Derivative of 5x squared is 10x. Leave the cosine x alone. Then leave the 5x squared alone times the derivative of cosine x, which is negative sine x. So right here I've got positive 5x squared times negative sine x. Right? Any like terms in there? Right here, see, x cosine x, 10 plus 10. So final answer, I've got 10 sine x plus 20x cosine x minus 5x squared sine x. And there's my second derivative on that one, okay? So there's an example of using sine and cosine derivatives in our normal everyday functions that we might run into. Let's talk about the other four trig functions now, because any of the six are going to come up all of the time when we're dealing with all of the functions that we are going to be doing derivatives with. So we need to have rules for all of them. Okay? So derivative of tangent x is equal to secant squared x. Let's see how this could be true. If I just have some function, y equals tangent x, right? To make this into something that I already am familiar with derivatives of, I can rewrite tangent as sine x over cosine x. Sine x over cosine x is one of those trig identities. Okay? So then my derivative, y prime, would be something I'm taking the derivative of here, but it's a quotient rule. But that's okay. At least it's familiar with sine and cosine. So let's do quotient rule. Low d high That's going to be cosine times cosine minus high d low. So high is sine, derivative of cosine is negative sine, all over square of what's below. So cosine squared. If you look really carefully at the top there, you should notice that what we've got is cosine squared plus sine squared. Because of the double negative, right? Cosine squared plus sine squared, one of your oldest trig identities, is 1 over cosine squared. And of course, 1 over cosine is secant, so 1 over cosine squared is secant squared. Incidentally, this exact same method is used to show that the derivative of cotangent is negative cosecant squared. Okay? I might point out that you may have noticed a pattern by now. Anytime I take the derivative of something that's a main trig function without the co in it, sine, tangent, or secant, notice they're always positive. And anytime I take a derivative with something with a co in it, cotangent, cosecant, cosine last time, they all have a negative in the pattern there. All right, so keep that in mind. All right, so derivative of tangent is secant squared. Derivative of secant is secant times tangent. I'm seeing a connection there too. Do you see how secant and tangent sort of feed off of each other? Just like sine and cosine feed off of each other, cotangent and cosecant are also going to feed off of each other. We have those little groupings. And that happens in trigonometry also with your Pythagorean identities, right? Secant squared is equal to 1 plus tangent squared, right? Secant and tangent have a really deep connection. So do cosecant and cotangent. So do sine and cosine. All right, so here, to show this derivative, I'll do something very similar. Secant is equal to 1 over cosine. So if I do y equals secant, that's 1 over cosine x, right? To do my derivative, y prime, again, I'll do a quotient rule. So low d high, cosine x times 0, minus high, which is 1, d low, which is negative sine, all over square of what's below, so that's cosine squared. Again, notice in the top, this piece is times 0, it's gone. Double negative is a positive. What I'm left with is y prime is equal to sine x over cosine squared x. But right here, what you should really see is that instead of writing it as cosine squared here, I'm going to write it as sine x over cosine x times 1 over cosine x. Because then I still have my cosine squared, right? And sine times 1 is going to give me sine x. But sine x over cosine x is tangent. And 1 over cosine is secant. So just as before, the derivative of secant is secant tangent, or secant x times tangent x. Okay? And again, very similar, you can do a derivative of cosecant and get negative cosecant times cotangent. Okay? So, example. Find, hey, what is all that garbage? What does that say? I see the d's, so we're thinking derivatives, right? And then there's some 2's in there, so it's probably second derivative, right? But why is there a t there? It's an independent variable, right? Z, in other words, must depend on t some kind of way. Well, there it is. Z is equal to cosecant of t. So we're finding the second derivative of z with respect to t. I'm just going to do 2 derivatives of t this time. All right, well, we've already seen the first derivative of cosecant. Step 1 is easy. Z prime, or let's go ahead and write it the way we have it here, dz dt is equal to negative cosecant of t times cotangent of t. Right? Okay? Now we want the second derivative, so I have to do the derivative of this derivative, right? Okay, so here we go. I've got d squared z dt squared is equal to, this is going to be a product rule, right? Because I have two things multiplied each with a variable. And then the negative is just going to be along for the ride. I'll go ahead and stick the negative with the cosecant. Okay? So, product rule. Derivative of the cosecant is negative cosecant of t times cotangent of t. That's the first derivative. The first piece is derivative, and then leave the cotangent alone, right? All right. Plus, leave this guy alone. That's negative cosecant of t times derivative of cotangent is negative cosecant squared. Alrighty. So second derivative of z with respect to t. Let's see what we've got. We've got negative, negative, so positive. I've got cosecant of t, cotangent squared of t. Over here, negative, negative also, so plus. And I've got cosecant cubed of t, right? And that's not a bad spot to stay. We could try factoring out an extra cosecant, right? That would give me cotangent squared plus cosecant squared. But cotangent squared plus cosecant squared doesn't have that nice of an identity. If it was cosecant squared minus cotangent squared, then we'd have something. This is not a bad place to leave this one. There are several things you can do, but we don't need to. Let's finish up with a few more examples of using trig mixed in with all of the other functions that we've been talking about so far. Okay? So, let's take a derivative of the function f that is equal to 3 secant x plus 5 over x squared. All right? So, remember, I've got a rule for secant x, no problem. But 5 over x squared, I need to rewrite first. So I'm going to have this equal to 3 secant x plus 5x to the negative 2 power. Don't forget, I haven't done any calculus yet, which is why I can still put the equals. Don't put equals if you've just taken a derivative. Those are not equal. So f prime, right, first derivative, is equal to derivative of secant, bring the 3 along for the ride, is secant times tangent. Yeah? Next, this is going to be one of those power rules. I'll drop the negative 2 times the 5. That'll give me negative 10. And then x has to not lose a power, but drop 1, right? So negative 2 minus 1 is negative 3. Okay, now in certain circumstances, it's okay to leave your answer in this form. Or, don't forget, you can also rewrite 3 secant x tangent x minus 10 over x to the 3rd power. Right? Either one of those is completely fine. All right, and then seems pretty simple in the next one, right? G of x is just sine of 2x. Except we didn't talk about taking a derivative of something that had another number on the inside. And in fact, we don't have the generic structural rule yet. That's the next lecture on chain rule. We haven't talked about what happens when you change something on the inside of a function, right? But luckily for us, we've got trig identities that will allow me to rewrite this into things that I can easily take the derivative of. Right? Sine of 2x is equal to 2 times sine x times cosine x. And then I've just got a product rule of the 2 sine x and the cosine x. All right, so here we go. dg dx, right? That's another way that I can write derivative. So I'll take the derivative of this first guy. That'll give me 2 cosine x, right? All right, and then leave the cosine alone. Plus, leave the first guy alone, 2 sine x, and then derivative of cosine is negative sine x, right? Let's condense a little. I now have 2 cosine squared of x minus 2 sine squared of x. But do you notice how they both have a 2? And I could just factor that out like this, right? And then cosine squared x minus sine squared x should look a little familiar to you. That's also one of those double angle identities. This is now equal to 2 cosine 2x. You could have left it in this other form, but it feels sort of appropriate here to go ahead and convert it back, because look at the relationship with the function that we started with originally and now what we have out here, right? It makes sense. The derivative of a sine should give me a cosine, and it also makes sense that that 2x should still be there, but what's extra is I've got this multiplied 2 out here, and we can explain that more, like I said, next lecture when we start talking about chain rule. But this is a perfect form to leave this derivative in. All right, and we seem to like this one an awful lot, right? Find the equation of a tangent line. We're going to have to do that a whole bunch throughout calculus. Plus, it also gives us a good excuse to not only find a derivative function, but to actually plug a value in and see what we get from a derivative function. Don't forget, we get a slope, right? That's what this whole derivative thing is about. I'm measuring change by measuring the instantaneous slope at a point, right? So they gave us our point and our function, and they want us to create a line tangent to the function, okay? So remember, what I'm going to eventually be doing is using point slope to create my line. M, of course, the slope is going to come from the derivative, and then x1 was already given to us, but I also need a y value, right? So my y value is going to be t of pi over 4. So tangent of pi over 4 divided by pi over 4 squared. Tangent of pi over 4. Tangent of pi over 4. You should remember that one, right? Tangent of pi over 4 is tangent of 45 degrees, which is 1. And in the bottom, I'm doing pi over 4 quantity squared. So I'm getting pi squared over 16 in the denominator. But it's 1 over that, right? So we'll just do the reciprocal. So my y value is going to be 16 over pi squared. And I'm going to leave it in that form because it could really get, a lot uglier from there. We're going to just leave it like that. So I've got my y value, right? That's going to be important later when I'm making the line. Let's get our derivative going. In fact, let me make a little space just in case here. Okay? So t prime of x. It's a quotient rule, right? You can see the fraction, and there's no way to simplify this any because I have a trig mixed with a polynomial, right? A transcendental with a non-transcendental, right? Okay, so I have to do quotient rule, which is low d high. That's going to be x squared times secant squared minus high d low. So that's going to be 2x times tangent x. High d low. It was just easier for me to write the 2x in front because that's typically what we do with trigonometry. all over square of below. That's just going to be x to the fourth because it's x squared squared, right? If it helps, write it out. It's going to be x squared squared, which is going to give me x to the fourth. Well, okay, let's do some factoring. Whenever you're doing a lot of these quotient rules and product rules, what you're going to find in these ones that can't be simplified before is you might get some of these repetitive objects that I can factor out and possibly even reduce since it is a fraction. Okay, so right here, I'm noticing that I can factor out a x, right? So t prime of x. I can factor an x out, and that leaves me with x times secant squared x minus 2 tangent x like this, divided by x to the fourth, right? Well, of course, I have a multiplied x in the front. I have divided x's in the denominator. This is going to reduce by one level. So my derivative function simplified looks like this. X times secant squared of x minus 2 tangent of x all over x cubed. Okay, but I'm interested in a particular value, right? So I'm going to be doing t prime of my x value, pi over 4. So t prime of pi over 4 is equal to x times the secant squared of x, so that's pi over 4, times secant squared of pi over 4, which, remember, what that really means is the secant of pi over 4, and then whatever that value is, squared. Remember, the squared on the secant is shorthand. Minus 2 times tangent pi over 4. And then I've got pi over 4 in the bottom, all cubed, like so. All right, let's see. Secant of pi over 4, right? Well, that's just 1 over the cosine of 45. Cosine of 45 is square root of 2 over 2, or 1 over square root of 2. So secant would be flipping that, which would be just square root of 2. But it's being squared, right? So here's what I've got. I've got pi over 4 times the square root of 2 squared, which is going to give me 2 times pi over 4. And of course, tangent of pi over 4 we already saw is 1. So I've got minus 2 over, I've got pi cubed over 64 in the bottom there. Okay, just a little bit more to simplify. I have pi over 2 minus 2 over pi cubed over 64. And what I'm going to do is I'm going to multiply by the 64 in all three places to simplify that, right? Here's what I'm going to do. I'm going to multiply by 64 here so that it wipes there. But that also means I have to multiply by 64 here and here. Okay? So my slope, I'll just go ahead and call it m, right? Because that's what we have. That's going to be 32 pi minus 128 all over pi cubed. There's my slope. Okay. So now for the real grand mess, right? I've got my slope. Now let's make the line. So y minus, I've got 16 over pi squared equals my slope, 32 pi minus 128 over pi cubed times x minus pi over 4. All right. So I'm going to distribute this, okay? I've got 16 over pi squared. I'm going to have 32 pi minus 128 over pi cubed times x. Now watch. When I'm going to have to multiply this times pi over 4, right? But I've got a pi in the top and 3 of them in the bottom, right? So I'm going to end up with 2 in the bottom, right? Because pi over pi cubed is just going to give me the pi squared in the denominator. Also, I'm going to be dividing the 32 and the 128 by -4. That's going to leave me, I'll go ahead and put a plus here, and I'll just have the negatives appropriately put here. That's going to leave me a -8 pi and plus, let's see, should be what, 32, huh? Because it'll be the 64, yeah, it should be 32. And it's plus, right, because of the double negative. Now I wrote it like that, but what I really want to do is go ahead and factor out that negative. No, I'm going to leave it. So watch. Now I've got to get the y by itself, right? Right here. I'll have y equals, and it's still going to be the 32 pi minus 128 over pi cubed, right? That's my slope times x. Okay? But I'm adding this to the other side so that I can get y by itself. So I'm going to add 16 over pi squared. Notice they already have a common denominator, right? And the 16 is going to combine with the 32 portion because they're like terms. 16 and 32 make 48. Let me write it an easier way. It's going to give me 48 minus 8 pi, like that. So I have number times x plus some number, right? This is the line that will be tangent to that function at that point, okay? So I hope this has helped you understand how we will take derivatives of trig functions. Stay tuned next for chain rule, which is another really important structural rule, and will really start to bring a lot more things together. Let's have some fun looking at what that graph actually looks like we just did that computation with. First thing you want to notice is that I have the x-axis numbered differently. By the way, if you're using GeoGebra, that's not hard to do. You can just go into the graphics settings under x-axis and tell it what you want the distance to be measured as. I typed in pi over 4 because I knew that that's what my x value was, and that's what a lot of our units were going to be in. Okay, so I've got my x-axis numbered in pi over 4s there. And let's take a look at the function. T of x is tangent x divided by x squared. Very interesting looking function there. Let me zoom out and give you a perspective real quick. You can see it's a very repetitive, mostly periodic, but be careful with, the shapes are a little different each time around. So it's not exactly like doing your normal periodic function. Right? You can see even the shapes on some of these are different than the next ones down. And obviously these are different. The point that we were interested in was when x was pi over 4 here. So here's that location on the graph right there. The t of pi over 4 we computed to be 16 divided by pi squared, the 1.62. And then we said that our tangent line was this interesting bunch of symbols, right? 32 pi minus 128 over pi cubed, all times x, plus 48 minus 8 pi over pi squared. So let's hit it. And there it is. You can see that this line is in fact tangent to the function t at that point when x is pi over 4.